Welcome to this quiet corner of the cosmos, where we explore the gentle mysteries of space and time. Tonight, we're following humanity's most distant messenger as it drifts through the vast emptiness between stars. Whether you're settling in for sleep beneath city lights or finding calm in the afternoon quiet, thank you for joining this peaceful journey into the depths of space. If you find comfort in these soft explorations of science, I invite you to subscribe. The universe holds countless stories, and we have all the time we need to discover them together. Before we begin, I'd love to know where you're listening from tonight and what time it is in your corner of the world. There's something beautifully fitting about discussing interstellar travel while we're all scattered across different time zones, each of us riding our own spinning world through the darkness. Picture this. Right now, as you listen to these words, a small spacecraft no larger than a compact car is traveling through space at over 38,000 miles per hour. It's been journeying for more than 4 decades, carrying with it the hopes and dreams of an entire species. This is Voyager 1, humanity's most distant ambassador, and tonight we'll follow its extraordinary voyage into the unknown. Launched on September 5th, 1977, Voyager 1 has traveled farther from Earth than any human-made object in history. It has crossed the boundary of our solar system, ventured into interstellar space, and continues its lonely journey toward the stars. But as it travels ever farther from home, we face a profound question. How far can it go before we lose contact forever? The story of Voyager 1 begins not with rockets and launch pads, but with a rare celestial alignment that occurs only once every 176 years. In the 1960s, scientists realized that the outer planets of our solar system would soon arrange themselves in a configuration that would allow a single spacecraft to visit multiple worlds using gravity assists. This cosmic dance of planets would create what mission planners called the Grand Tour, an opportunity to explore the outer reaches of our solar system with unprecedented efficiency. The concept was elegant in its simplicity. A spacecraft launched toward Jupiter could use the giant planet's immense gravitational field to accelerate and change direction, much like a slingshot. This gravitational assist would propel the craft towards Saturn, where another encounter could send it on to Uranus and Neptune. Each planetary encounter would add speed and alter the trajectory, creating a cosmic relay race through the outer solar system. Originally conceived as the Grand Tour mission, budget constraints forced NASA to scale back the ambitious plan. Instead, they approved the Voyager program, consisting of 2 identical spacecraft that would visit Jupiter and Saturn, with the possibility of continuing to Uranus and Neptune if the primary mission succeeded. It was a compromise that would ultimately lead to one of the most successful space missions in history. The timing was crucial. The planetary alignment that made the Grand Tour possible would not occur again until the 22nd century. If humanity was to seize this opportunity, it had to act in the 1970s. The window was narrow and the stakes were high. This was our chance to explore the outer solar system in detail, to see worlds that had been nothing more than points of light in our telescopes. Voyager 1 and its twin, Voyager 2, were marvels of 1970s engineering. Each spacecraft weighed about 825 kilograms and carried a suite of scientific instruments designed to study the magnetic fields, charged particles, and cosmic rays they would encounter. Their cameras would capture the first detailed images of the outer planets and their moons, while their other instruments would measure everything from temperature to radio emissions. But perhaps the most poetic aspect of the Voyager missions was the inclusion of the Golden Record, a 12-inch gold-plated copper disc containing sounds and images from Earth. Carl Sagan and his team carefully selected the contents. Music from Bach and Beethoven, greetings in 55 languages, sounds of wind and rain, and photographs of human life and culture. It was a message in a bottle, cast into the cosmic ocean with the hope that someday, somewhere, another intelligence might find it and learn about the small blue world that created it. The Golden Record was more than just a scientific instrument. It was an act of profound optimism. It acknowledged that Voyager 1 would eventually leave our solar system entirely, becoming an interstellar wanderer. Long after its instruments fell silent, long after contact with Earth was lost, the spacecraft would continue its journey, carrying with it a piece of humanity into the vast unknown. As Voyager 1 embarked on its grand tour, it began a journey that would redefine our understanding of the outer solar system. Its first major encounter was with Jupiter in March 1979, where it discovered active volcanoes on the moon Io and revealed the complex ring system surrounding the giant planet. The images it sent back were breathtaking, showing Jupiter's great red spot in unprecedented detail and revealing the intricate dance of its many moons. The spacecraft's encounter with Saturn in November 1980 was equally spectacular. Voyager 1 provided the first detailed look at Saturn's rings, revealing thousands of individual ringlets and discovering new moons. The images of Saturn, with its majestic rings backlit by the sun, remain some of the most beautiful photographs ever taken in space. But for Voyager 1, the Saturn encounter marked the end of its planetary tour. The spacecraft's trajectory took it out of the plane of the solar system, beginning its long journey toward interstellar space. From this point forward, it would be traveling alone, with no more planets to visit, no more gravitational assists to speed it on its way. As Voyager 1 continued its journey beyond Saturn, it entered a new phase of its mission. The spacecraft was now traveling through the outer reaches of the solar system, a region dominated by the solar wind, a stream of charged particles flowing from the sun. This solar wind creates a bubble around our solar system called the heliosphere, and Voyager 1 was heading directly toward its boundary. The heliosphere is vast, extending far beyond the orbit of Pluto. It's a region where the sun's influence gradually weakens, where the solar wind slows and eventually meets the interstellar medium, the thin soup of gas and dust that exists between the stars. The boundary of the heliosphere is called the heliopause, and crossing it would mark Voyager 1's entry into true interstellar space. As the spacecraft traveled through this region, its instruments continued to function, sending back data about the magnetic fields, cosmic rays, and charged particles it encountered. The journey was slow, measured not in days or months, but in years and decades. Each year, Voyager 1 traveled farther from the Sun than Earth's entire orbital diameter. Yet it would take decades to reach the heliopause. The spacecraft's power source, a radioisotope thermoelectric generator, slowly declined over the years. Unlike solar panels, which would be useless in the dim outer solar system, the RTG converted the heat from radioactive decay into electricity. But the radioactive material was steadily decaying, and the power output decreased by about 4 watts per year. As the power declined, mission controllers had to make difficult decisions about which instruments to keep operating. One by one, non-essential systems were shut down to conserve power for the most critical instruments. The spacecraft's cameras were turned off in 1990 after taking the famous pale blue dot photograph that showed Earth as a tiny speck in the cosmic darkness. The gradual loss of power was not the only challenge facing Voyager 1. The spacecraft's distance from Earth meant that radio signals took increasingly longer to travel between the craft and mission control. By the time Voyager 1 reached the outer solar system, it took over 10 hours for a signal to travel from Earth to the spacecraft, and another 10 hours for a response to return. This communication delay made real-time control of the spacecraft impossible. Every command had to be planned carefully, with mission controllers unable to make quick corrections if something went wrong. The spacecraft had to be increasingly autonomous, relying on its onboard computers to make decisions about its operation. Despite these challenges, Voyager 1 continued its journey, steadily approaching the boundary of the solar system. Scientists eagerly awaited the moment when it would cross the heliopause and enter interstellar space. It would be a historic milestone, the first time a human-made object had left the solar system and entered the realm of the stars. The crossing of the heliopause was not a sudden event, but a gradual transition. As Voyager 1 approached the boundary, its instruments detected changes in the magnetic field and the density of charged particles. The solar wind began to weaken, and the spacecraft entered a region where the interstellar medium began to dominate. On August 25, 2012, Voyager 1 officially crossed the heliopause and entered interstellar space. It was a moment of triumph for the mission team and for humanity as a whole. After 35 years of travel, covering more than 11 billion miles, Voyager 1 had become the first human-made object to leave the solar system. But this achievement also marked the beginning of a new phase in the mission's life, one defined by the gradual loss of contact with Earth. As Voyager 1 continues its journey into interstellar space, it faces the ultimate question: how far can it go before we lose contact forever? The answer to this question lies in the delicate balance between the spacecraft's declining power and the sensitivity of the radio telescopes on Earth. The silence between Earth and Voyager 1 grows longer with each passing day. As you settle into the comfort of your evening routine, perhaps checking messages on your phone or listening to the familiar sounds of your neighborhood, imagine the profound quiet that surrounds this tiny spacecraft, now over 14 billion miles from home. The signals we send to Voyager 1 today take more than 22 hours to reach it, traveling at the speed of light across the vast emptiness of space. When the spacecraft responds, if it responds, another 22 hours pass before we hear its whispered reply. A simple conversation that might take seconds between you and a friend now requires nearly 2 full days to complete. This growing communication delay represents just one of the mounting challenges that threaten our connection to humanity's most distant ambassador. Every year, Voyager 1 travels roughly another 300 million miles farther from Earth, stretching the invisible tether that binds us to this remarkable machine. The mathematics are both beautiful and sobering in their simplicity. As distance increases, the strength of radio signals decreases by the square of that distance. Double the distance, and the signal becomes 4 times weaker. Triple it, and the signal weakens by a factor of 9. Voyager 1 has already traveled so far that its transmissions arrive at Earth with a power of just 20 billion billionths of a watt, roughly equivalent to the energy required to light a single snowflake as it melts. The Deep Space Network, that collection of massive radio antennas scattered across Earth's surface in California, Spain, and Australia, strains to catch these ethereal whispers from the void. These engineering marvels, some as large as football fields, rotate slowly to track Voyager's position as our planet spins through its daily cycle. The largest of these dishes, the 70-meter antenna at Goldstone, California, can detect signals so weak they would be overwhelmed by the electromagnetic radiation from a cell phone on Mars. Yet even these technological giants are approaching the limits of what physics allows. The cosmic background radiation that permeates all of space creates a constant static that grows more problematic as Voyager's signals continue to fade, but distance and signal strength tell only part of this melancholy story. Aboard Voyager 1, 3 radioisotope thermoelectric generators slowly consume their nuclear fuel, converting the heat from radioactive decay into the electrical power that keeps the spacecraft alive. These generators, marvels of engineering that have operated flawlessly for over 4 decades, lose approximately 4 watts of power each year. When Voyager 1 launched in 1977, these generators produced roughly 470 watts of electricity. Today, that number has dwindled to less than 250 watts, barely enough to power a few household light bulbs. This gradual power decline forces mission engineers to make increasingly difficult choices, about which systems to keep running and which to shut down forever. The spacecraft's heaters, designed to protect delicate instruments from the frigid cold of space, have been turned off one by one. The scan platform that allowed Voyager to point its cameras and instruments with precision was powered down years ago, its work complete. Various scientific instruments have been placed into hibernation mode or switched off entirely, their data collection missions ending not with fanfare, but with the quiet click of a relay switching to the off position. The cold of interstellar space presents its own relentless challenge. At Voyager 1's current location, temperatures hover around 270 deg, just a few degrees above absolute zero. This is cold beyond earthly comprehension, cold enough to freeze nitrogen and oxygen solid, cold enough to make metals brittle as glass. The spacecraft's electronic components, designed and tested in Earth's comparatively warm environment, operate in conditions their creators could simulate, but never fully anticipate over such extended periods. Perhaps most poignantly, the very success of Voyager 1's mission contributes to the challenges it now faces. The spacecraft was designed for a 4-year mission to Jupiter and Saturn. Every day it continues to operate represents a triumph of engineering redundancy and careful planning, but also pushes systems far beyond their intended operational lifetime. Components that were expected to function for a few years now soldier on, after more than 4 decades, their performance slowly degrading in ways that engineers can monitor but cannot repair across the vast distance of space. The trajectory that carries Voyager 1 away from Earth is as relentless as it is beautiful. The spacecraft travels at roughly 38,000 miles per hour relative to the Sun, fast enough to cross the continental United States in about 4 minutes. This speed, gained through careful gravitational assists from Jupiter and Saturn decades ago, cannot be changed. There are no fuel reserves for course corrections, no way to slow down or turn around. Voyager 1 is committed to its path through the galaxy, following an orbit that will take it gradually closer to the constellation Ophiuchus over the next 40,000 years. This trajectory carries Voyager 1 not just away from Earth, but away from the Sun itself, into regions of space where solar energy becomes negligible and the influence of other stars begins to assert itself. The spacecraft is entering what astronomers call the local interstellar cloud, a region of space filled with gas and dust from ancient stellar explosions. This environment, while still incredibly sparse by earthly standards, is nonetheless denser than the solar wind-dominated region Voyager 1 left behind when it crossed the heliopause. This increased density could potentially affect the spacecraft's trajectory over very long time periods, though such changes would be imperceptible during our current communication window. The instruments still operating aboard Voyager 1 continue to send back data about this alien environment, measurements that no other human-made object has ever been able to provide. The plasma wave subsystem detects oscillations in the charged particles around the spacecraft, revealing the density and movement of interstellar matter. The magnetometer measures magnetic fields that may have been shaped by stellar winds from distant stars. The cosmic ray subsystem counts high-energy particles that have traveled across the galaxy, some perhaps originating from supernova explosions that occurred before our solar system was born. Each piece of data transmitted back to Earth represents a small victory against the growing obstacles. The information travels as radio waves, electromagnetic radiation that moves at the speed of light, but still requires those 22 hours to bridge the gap between spacecraft and home. These signals, when they finally reach Earth, are captured by the Deep Space Network's antennas and carefully processed to extract every bit of scientific information they contain. The data rates have been reduced multiple times over the years to conserve power and ensure signal reliability, but the stream of discoveries continues. Mission controllers at the Jet Propulsion Laboratory in California maintain a careful vigil over Voyager 1's health, monitoring its systems and planning for the inevitable decisions that lie ahead. These engineers and scientists, many of whom were not even born when Voyager 1 launched, have inherited responsibility for humanity's most distant explorer. They study telemetry data, plan software updates that must be transmitted across billions of miles, and prepare for the day when difficult choices must be made about which instruments to sacrifice to extend the mission's life. The spacecraft's computer systems, based on technology from the 1970s, continue to operate with a reliability that modern smartphone users might find difficult to believe. The main computer has less memory than a basic calculator, yet it continues to manage complex scientific observations, maintain communication with Earth, and monitor the spacecraft's health. Software updates, when necessary, must be planned months in advance and transmitted with careful redundancy to ensure they arrive intact across the vast distance. As power continues to decline and systems age, mission planners face increasingly creative challenges. They must balance the scientific value of different instruments against their power consumption, sometimes choosing to turn off one experiment to keep another running for a few more years. They monitor temperature readings throughout the spacecraft, watching for signs that critical components might be approaching their operational limits. They plan communication schedules that maximize data return while conserving both power and the limited time when Earth's massive antennas can point toward Voyager's position in space. The end of communication with Voyager 1, when it comes, will likely not arrive as a dramatic failure, but as a gradual fade. The spacecraft's transmitter will continue to broadcast, but its signals will become too weak for Earth's receivers to detect above the background noise of space. Alternatively, the onboard power may drop below the level needed to operate the radio transmitter, leaving Voyager 1 alive but silent, continuing its journey through the galaxy without the ability to share its discoveries with the world that built it. Current projections suggest that meaningful communication with Voyager 1 may end sometime in the late 2020s or early 2030s, though this timeline depends on many variables including the health of individual components, decisions about power management, and potential improvements to Earth-based receiving equipment. Some instruments may continue operating into the mid-2030s if power management strategies prove successful and no critical systems fail unexpectedly. When that final signal is received, when the last whisper from Voyager 1 fades into the cosmic background noise, the spacecraft will continue its journey in silence. It will pass within roughly 1.5 light years of the star Gliese 445 in about 40,000 years, closer to another star than it is to our Sun today. In about 300,000 years, it will reach the inner edge of the Oort cloud, that vast spherical shell of icy objects that marks the outermost boundary of our solar system's gravitational influence. But for now, in this precious window of time, Voyager 1 continues to transmit its discoveries across the growing void. Each signal represents a triumph of human ingenuity and determination, a message from the edge of known space that reminds us of our capability to reach beyond the boundaries of our small world. Voyager 1, the fading signal. The Deep Space Network antenna at Goldstone, California, rotates slowly through the desert night, its massive dish pointed toward a region of space so distant that the very concept of distance begins to lose meaning. Somewhere in that darkness, over 14 billion miles from Earth, a small spacecraft, no larger than a compact car, continues its solitary journey through the interstellar medium. This is Voyager 1, humanity's most distant ambassador, and every day it drifts a little further from home, its signal growing a little weaker, bringing us closer to an inevitable moment of silence. The spacecraft's radioisotope thermoelectric generators have been steadily declining in power for decades now, their plutonium-238 fuel slowly decaying with the patient inevitability of atomic physics. Each year, Voyager 1 loses about 4 watts of power, roughly equivalent to a small LED bulb. It might not sound like much, but in the harsh environment of interstellar space, every watt is precious. Every bit of electricity carefully rationed between the essential systems that keep this ancient traveler functioning. Mission controllers at the Jet Propulsion Laboratory face increasingly difficult decisions about which instruments to keep operational and which to sacrifice. The attitude control thrusters, those tiny rockets that keep Voyager properly oriented toward Earth, require power. The radio transmitter that carries the spacecraft's whispered data across the cosmic void needs electricity. The computer systems that process and format the scientific observations demand their share of the dwindling energy budget. One by one, over the years, instruments have been switched off forever. The infrared interferometer spectrometer fell silent in 1998. The photopolarimeter was shut down in 1998. The planetary radio astronomy experiment ceased operations in 2007. Each shutdown represents not just a loss of scientific capability, but a small death, a gradual diminishment of this remarkable machine's ability to sense and report on the universe around it. But the signal itself, that faint carrier wave that connects Voyager 1 to Earth, faces challenges beyond mere power limitations. The inverse square law of physics dictates that radio signals weaken with the square of the distance traveled. As Voyager 1 moves further from Earth, its signal becomes exponentially fainter. What began as a robust communication link in 1977 has become a whisper that requires the most sensitive receivers on Earth to detect. 7 meters across must point directly at Earth to maintain contact. But Earth is not a fixed point in space. Our planet orbits the Sun, rotating on its axis, following a complex path through the solar system. Voyager 1's guidance systems must constantly adjust for this motion, burning precious fuel to maintain the precise orientation required for communication. Distance introduces another cruel factor into this cosmic conversation: time delay. When Voyager 1 was launched, radio signals took mere minutes to travel between spacecraft and Earth. Now, those signals must cross nearly 23 light-hours of space. A command sent today will not reach Voyager 1 until tomorrow. The spacecraft's response will not return until the day after that. This growing delay transforms every interaction into a carefully choreographed dance of patience and prediction. The interstellar medium itself presents obstacles to communication. Unlike the relative emptiness of the solar system, the space between stars contains wisps of gas and dust, charged particles, and magnetic fields that can scatter and absorb radio waves. As Voyager 1 penetrates deeper into this cosmic fog, its signals must push through an increasingly complex electromagnetic environment. Ground-based receivers face their own limitations. The Deep Space Network's largest antennas, those 70-meter giants in California, Spain, and Australia, represent the pinnacle of human engineering. Yet even these magnificent instruments struggle to extract Voyager's faint signal from the background noise of the universe. Solar storms can overwhelm the delicate receivers. Equipment failures can temporarily sever the connection. The constant rotation of the Earth means that no single antenna can maintain contact with Voyager continuously. NASA engineers have performed remarkable feats of ingenuity to extend the mission's life. They've reprogrammed 40-year-old computers using programming languages that today's software engineers barely remember. They've switched to backup systems that were never intended for routine use. They've found ways to squeeze more power from the failing generators, more sensitivity from the ancient receivers, more life from systems that were designed for a 4-year mission to Jupiter and Saturn. The Voyager team has become a group of digital archaeologists, maintaining communication with a spacecraft older than many of the engineers who operate it. They work with documentation written on paper, programming tools that predate the personal computer, and hardware that represents the cutting edge of 1970s technology. Every day brings new challenges as components age, software encounters unexpected conditions, and the harsh environment of space takes its toll on systems never designed for such longevity. Yet despite these mounting challenges, Voyager 1 continues to return scientific data about the interstellar environment. Its cosmic ray detector measures high-energy particles streaming through space. Its magnetometer senses the magnetic fields that permeate the galaxy. Its plasma wave instrument listens to the electrical symphonies of charged particles in the interstellar medium. Each measurement adds to our understanding of the galaxy beyond our solar system, knowledge that could not be obtained any other way. The spacecraft's journey through interstellar space has revealed a universe more complex and dynamic than scientists expected. The boundary between solar and interstellar space proved to be not a simple wall, but a complex transition zone where the solar wind struggles against the pressure of interstellar gas. The interstellar medium itself shows structure and variation, with regions of different density and magnetic field strength. As Voyager 1 moves through this alien environment, it serves as humanity's first probe of truly interstellar space. The data it returns helps scientists understand the local galactic neighborhood, the properties of the interstellar medium, and the interaction between our solar system and the galaxy at large. This information has implications for understanding stellar formation, galactic evolution, and the cosmic environment that shaped our solar system billions of years ago. The gradual loss of contact with Voyager 1 represents more than just the end of a scientific mission. It symbolizes humanity's first tentative step into the galaxy, a small but significant expansion of our presence beyond the solar system. The spacecraft carries the golden record, a message intended for any extraterrestrial intelligence that might encounter it in the distant future. As contact fades, Voyager 1 will become a silent ambassador, carrying human culture and knowledge through the galaxy long after our civilization has transformed beyond recognition. Current projections suggest that Voyager 1 will lose the ability to communicate with Earth sometime between 2025 and 2030. The exact date depends on many factors: the rate of power decline, the sensitivity of ground-based receivers, the spacecraft's ability to maintain proper orientation, and the success of ongoing engineering efforts to extend the mission. Each year brings new assessments and revised predictions as mission planners balance the competing demands of scientific instruments and essential systems. When the final signal is received, it will mark the end of one of humanity's greatest adventures. Voyager 1 will continue its journey into the galaxy, but it will travel in silence, carrying its precious cargo of human knowledge and culture into the cosmic deep. The spacecraft will pass within a few light years of other stars, drift through the galactic disk, and eventually orbit the center of the Milky Way, completing one galactic revolution every 225 million years. In the vast scales of cosmic time, Voyager 1's journey has barely begun. The spacecraft will outlive the Sun, continuing its silent voyage through a galaxy populated by alien stars and unknown worlds. It will witness the birth and death of stellar generations, the collision of galaxies, and the slow evolution of the universe itself. The golden record will remain intact for billions of years, a testament to a species that once looked up at the stars and dared to reach beyond their home world. The story of Voyager 1 reminds us that all journeys eventually end, all signals eventually fade, and all connections eventually break. But the journey itself, the courage to venture into the unknown, the knowledge gained along the way, and the hope carried forward into the future remain as humanity's greatest achievements. As we drift deeper into the story of Voyager 1's remarkable journey, we encounter one of the most fascinating aspects of its mission: the profound challenges of communicating across the vast emptiness of interstellar space. Picture, if you will, the delicate dance of radio waves traveling through the cosmic void, carrying whispers of data from humanity's most distant messenger back to our small blue world. The communications system aboard Voyager 1 represents a triumph of engineering simplicity and reliability. Built in an era when computer processors were measured in kilobytes rather than gigabytes, the spacecraft carries a high-gain antenna that must be precisely pointed toward Earth to maintain contact. 7 meters in diameter, serves as Voyager's voice across the interstellar medium, transmitting at a power level of just 23 watts, less than a household light bulb. Consider for a moment the extraordinary nature of this communication link. When Voyager 1 transmits a signal to Earth, those radio waves must travel more than 14 billion miles through space, spreading and weakening with each passing second. By the time they reach our planet, the signal strength has diminished to an almost incomprehensible level, approximately 20 billion times weaker than the power required to operate a digital watch. The Deep Space Network, NASA's collection of massive radio telescopes scattered across the globe, must strain to detect these faint whispers from the edge of known space. The journey of each radio signal from Voyager 1 to Earth takes approximately 22 hours, a delay that continues to grow longer as the spacecraft ventures further into interstellar space. This means that when mission controllers send a command to Voyager 1, they must wait nearly 2 days to receive confirmation that the spacecraft has received and executed their instructions. It's a conversation conducted in slow motion across the cosmos, where each exchange of information requires the patience of entire days. The data transmission rate has decreased dramatically over the decades. In the early years of the mission, Voyager 1 could send information at rates of thousands of bits per second. Now, operating at the limits of its power systems and communication capabilities, the spacecraft transmits at a rate of just 160 bits per second, slower than the most primitive dial-up internet connections. Each photograph, each scientific measurement, each piece of telemetry must be carefully prioritized and transmitted in tiny fragments across the interstellar gulf. The radio waves themselves face obstacles that would be unimaginable in terrestrial communications. The interstellar medium, though incredibly tenuous, contains enough charged particles and magnetic fields to subtly affect the propagation of radio signals. Solar storms and electromagnetic interference from our own sun can occasionally overwhelm the weak transmissions from Voyager 1, creating periods of silence that test the patience and ingenuity of mission controllers. Perhaps most remarkably, the spacecraft's communications system has endured conditions that would destroy most Earthbound electronics. The temperature variations range from the scorching heat of direct sunlight to the bone-chilling cold of interstellar space. Cosmic radiation bombards the electronics continuously, gradually degrading components and occasionally causing temporary malfunctions. The fact that Voyager 1 can still communicate at all after more than 4 decades in space represents an extraordinary testament to the engineering prowess of its creators. The ground-based portion of this communication link is equally impressive. The Deep Space Network consists of 3 complexes strategically positioned around the globe in California, Spain, and Australia. These locations ensure that at least one antenna is always pointing toward any given spacecraft as Earth rotates. The largest of these antennas, measuring 70 meters in diameter, are among the most sensitive radio receivers ever constructed, capable of detecting signals so weak they would be completely overwhelmed by the electromagnetic noise of a nearby cell phone. The process of receiving and decoding Voyager 1 signals requires extraordinary precision and patience. Engineers must account for the Doppler shift caused by the spacecraft's motion, the relativistic effects of its high speed, and the subtle variations in signal strength caused by the spacecraft's slow tumbling motion. Each data packet must be carefully reconstructed from the fragments that arrive, with sophisticated error correction algorithms working to recover information that may have been corrupted during its billion-mile journey. The gradual degradation of Voyager 1's power systems adds another layer of complexity to the communication challenge. The spacecraft's radioisotope thermoelectric generators lose approximately 4 watts of power each year as their plutonium fuel naturally decays. This steady decline in available power forces mission controllers to make increasingly difficult decisions about which systems to keep operational and which to shut down permanently. Each instrument that falls silent represents not just a loss of scientific capability, but a step closer to the inevitable moment when Voyager 1 will no longer have enough power to maintain contact with Earth. The temperature of the spacecraft's electronics compartment is maintained by carefully managing the waste heat from its power systems and instruments. As power levels decline, this thermal management becomes increasingly challenging. Some components may fail, not from age or radiation damage, but simply from operating outside their designed temperature ranges. The spacecraft's ability to point its antenna toward Earth depends on attitude control systems that consume precious power, creating a delicate balance between maintaining communication and preserving the energy needed for that very communication. Despite these mounting challenges, Voyager 1 continues to send back valuable scientific data about the nature of interstellar space. Its instruments measure the density of particles in the interstellar medium, the strength and direction of magnetic fields, and the flux of cosmic rays that permeate the galaxy. Each measurement provides insights into the environment that our solar system moves through as it orbits the center of the Milky Way galaxy. The spacecraft's plasma wave instrument has detected the sounds of interstellar space itself, recording the subtle vibrations that propagate through the thin gas between stars. These acoustic waves, though far too low in frequency for human ears to detect, provide information about the structure and dynamics of the interstellar medium. When converted to audible frequencies, they create haunting, ethereal tones that represent the actual sounds of the space between stars. Voyager 1's magnetic field measurements have revealed the complex structure of the heliosphere's boundary region, where the solar wind meets the interstellar medium. This data has helped scientists understand how our solar system interacts with the broader galactic environment, and how the sun's influence gradually fades with distance. The spacecraft has discovered that the magnetic field in local interstellar space is stronger than expected, suggesting that our solar system may be moving through a region of space with unusual properties. The cosmic ray detectors aboard Voyager 1 have measured the dramatic increase in high-energy particles that occurs beyond the heliopause. These cosmic rays, accelerated by distant supernovae and other violent cosmic events, are largely blocked by the solar wind within our heliosphere. The measurements from interstellar space provide direct information about the background radiation environment that pervades our galaxy, offering insights into the processes that accelerate particles to nearly the speed of light. As Voyager 1 continues its journey into the unknown, its communication link with Earth becomes increasingly tenuous. The spacecraft's transmissions grow weaker with each passing year, requiring ever more sensitive receivers and sophisticated signal processing techniques to decode. Mission controllers estimate that meaningful communication with Voyager 1 will become impossible sometime between 2025 and 2030, when the spacecraft's power levels drop below the threshold needed to operate its radio transmitter. The eventual loss of contact with Voyager 1 will mark the end of humanity's first direct exploration of interstellar space, but it will not mark the end of the spacecraft's journey. Long after its radio falls silent, Voyager 1 will continue traveling through the galaxy, carrying with it the golden record and the hopes of a species that dared to reach beyond the boundaries of its home. 6. Light years of the star AC +79 3888, though by then its radioactive power sources will have long since decayed and its instruments will have fallen silent. The story of Voyager 1's communication with Earth represents one of the most remarkable achievements in the history of human exploration. For more than 4 decades, this small spacecraft has maintained a tenuous but vital link across the vast emptiness of space, sending back information that has revolutionized our understanding of the solar system and beyond. As we contemplate the eventual silence that will mark the end of this extraordinary conversation, we can take comfort in knowing that Voyager 1 will continue its mission as humanity's ambassador to the cosmos, carrying our message to the stars long after we have lost the ability to hear its voice. The gradual fading of Voyager 1's signal serves as a poignant reminder of the immense scales involved in interstellar exploration. Each day that passes sees the spacecraft travel further from home, its radio waves growing weaker and its journey more solitary. Yet in this growing silence, there is also a profound beauty, a testament to human ingenuity and our irrepressible desire to explore the unknown. The vast emptiness between stars holds secrets that challenge our deepest understanding of physics and reality. As we continue our journey through the cosmos, we find ourselves confronting one of the most profound mysteries of our time: the nature of the invisible scaffolding that holds the universe together. You see, when astronomers first began measuring the rotation of galaxies in the 1970s, they discovered something that shouldn't have been possible according to our understanding of gravity. Stars at the outer edges of galaxies were moving far too quickly. By all rights, they should have been flung out into the cosmic void, scattered like sparks from a spinning wheel. Yet there they remained, held in their graceful orbits by something we couldn't see. This invisible something has come to be known as dark matter, and it represents one of the greatest puzzles in modern astrophysics. Despite making up roughly 27% of all matter and energy in the universe, dark matter interacts with ordinary matter only through gravity. It doesn't emit light, doesn't absorb light, and doesn't reflect light. It's essentially transparent to the electromagnetic spectrum, revealing itself only through its gravitational effects on the visible matter around it. The evidence for dark matter extends far beyond the rotation curves of individual galaxies. When we observe massive galaxy clusters, we can see the gravitational lensing effect they create, bending and distorting the light from more distant galaxies behind them. This lensing tells us about the total mass of these clusters, and consistently, we find that there's about 5 times more mass present than we can account for with visible matter alone. The missing mass reveals itself as a ghostly presence, shaping the paths of light across cosmic distances. Computer simulations of structure formation in the early universe provide perhaps the most compelling evidence for dark matter's existence. Without this invisible component, the tiny fluctuations in density that we observe in the cosmic microwave background radiation simply couldn't have grown into the vast cosmic web of galaxies and galaxy clusters we see today. Dark matter provides the gravitational framework upon which ordinary matter could condense and eventually form the first stars and galaxies. The search for dark matter has led scientists down fascinating theoretical paths. Some propose that dark matter consists of weakly interacting massive particles, or WIMPs, that were created in the earliest moments after the Big Bang. These hypothetical particles would rarely interact with ordinary matter, making them incredibly difficult to detect directly. Deep underground laboratories around the world house sensitive detectors, waiting patiently for the rare collision between a dark matter particle and ordinary atoms. Other theories suggest that dark matter might be composed of axions, theoretical particles so light and weakly interacting that they would behave more like waves than particles on cosmic scales. Still, others propose that our understanding of gravity itself might be incomplete, and that modifications to Einstein's general relativity could explain the observed phenomena without requiring additional invisible matter. The cosmic web that dark matter creates is a structure of breathtaking beauty and complexity. Like a three-dimensional spider's web spanning billions of light years, filaments of dark matter connect massive nodes where galaxy clusters form. Between these filaments lie vast voids, regions so empty that a galaxy wandering through such a space would be profoundly isolated, its nearest neighbors tens of millions of light years away. Along these dark matter highways, ordinary matter flows like rivers of gas and dust, eventually pooling in the gravitational wells where galaxies can form. The Milky Way itself sits within one such filament, connected through invisible threads to neighboring galaxies, hundreds of millions of light years away. Our local group of galaxies, including Andromeda and dozens of smaller companions, occupies a relatively dense region of this cosmic web. The interplay between dark matter and ordinary matter creates a dynamic, evolving universe. As dark matter structures grow through gravitational attraction, they provide the scaffolding for gas to cool and condense, eventually forming the stellar nurseries where new generations of stars are born. The feedback from these stars, through stellar winds and supernova explosions, can in turn influence the distribution of matter on galactic scales. Perhaps most remarkably, dark matter appears to be crucial for the formation of the first stars in the universe. In the early cosmos, before heavy elements existed, the only way for gas to cool and condense was through the gravitational influence of dark matter. These first dark matter halos provided the gravitational wells necessary for hydrogen and helium to collapse and ignite nuclear fusion, creating the very first sources of light in the cosmic dark age. The distribution of dark matter also influences the fate of galaxies over cosmic time. Galaxies falling into massive dark matter halos associated with galaxy clusters experience ram pressure stripping, where the hot intracluster medium tears away their gas reserves, eventually quenching star formation. Meanwhile, galaxies in less dense environments can continue forming stars for billions of years longer. Current observations suggest that dark matter particles, whatever they may be, interact with each other even more weakly than they interact with ordinary matter. This creates what astronomers call collisionless systems, where dark matter particles pass through each other like ghosts, creating structures that are fundamentally different from anything we experience in our everyday world. The mystery deepens when we consider that dark matter's gravitational effects are perfectly consistent with Einstein's general relativity, yet the particles themselves remain completely elusive. This has led some researchers to propose that dark matter might exist in a separate sector of physics, connected to our world only through gravity. Such hidden sector dark matter could have its own rich physics, with dark matter particles interacting through forces we know nothing about. As we continue to probe the nature of dark matter through increasingly sophisticated experiments and observations, we're reminded that the universe is far stranger and more wonderful than our ancestors could have imagined. The invisible scaffolding that holds galaxies together and guides the flow of matter across cosmic distances represents one of the greatest mysteries in science, a puzzle that may ultimately reveal new fundamental physics beyond our current understanding. Tonight, as you drift towards sleep, remember that you are surrounded by this invisible ocean of dark matter. Dark matter particles are streaming through your body, through the Earth, through the solar system, leaving no trace of their passage except for the gentle gravitational influence that helped shape the very galaxy in which you live. The cosmic web that connects the most distant galaxies also connects you to the grand architecture of the universe itself. In the morning, when you wake, the dark matter will still be there, patient and persistent, continuing its ancient work of sculpting the cosmos. Voyager 1. The Deepening Silence. As we've witnessed, Voyager 1 has already begun its slow fade from our cosmic conversation. The spacecraft continues its journey through the interstellar medium, but each passing year brings new challenges that test the limits of both human engineering and the fundamental physics of long-distance communication. The question isn't simply when we'll lose contact, but rather how far this remarkable messenger can travel before the universe itself imposes its final silence. The mathematics of Voyager's decline tell a story of inevitable entropy. The spacecraft's radioisotope thermoelectric generators lose approximately 4 watts of power each year, a steady hemorrhaging of energy that cannot be stopped or reversed. This isn't merely a technical limitation, but a fundamental consequence of radioactive decay, as predictable as the orbit of planets and as inexorable as the expansion of the universe itself. By the late 2020s, Voyager 1 will likely lack sufficient power to operate any of its scientific instruments, though it may continue transmitting a carrier signal for perhaps another decade. Yet power is only one constraint in this cosmic equation. The inverse square law governs how Voyager's signals weaken with distance, spreading their energy across ever larger spheres of space. At its current distance of over 160 astronomical units from Earth, Voyager's transmissions arrive with a power measured in attawatts, requiring the most sensitive receivers humanity has ever constructed. The Deep Space Network's massive antennas, some stretching 70 meters across, strain to capture these whispers from the edge of the solar system. The interstellar medium itself presents obstacles that early mission planners could scarcely imagine. Unlike the relatively empty space between planets, the region beyond the heliopause contains clouds of ionized gas that can scatter radio waves and create interference. Voyager 1 has already encountered variations in plasma density that affect signal propagation, and as it ventures deeper into interstellar space, these effects may become more pronounced. The spacecraft is essentially swimming through an ocean of charged particles, each interaction subtly altering its electromagnetic environment. Temperature variations also play a crucial role in Voyager's longevity. As the spacecraft's power output decreases, maintaining optimal operating temperatures becomes increasingly difficult. Critical components must be kept within narrow temperature ranges to function properly, and the mission team has already begun shutting down non-essential systems to conserve both power and heat. It's a delicate balance between extending the mission's duration and preserving the most vital functions. The communication delays themselves present unique challenges. Radio signals from Voyager 1 now take over 22 hours to reach Earth, meaning that any command sent to the spacecraft requires nearly 2 days for a complete round-trip communication. This delay will continue to grow as Voyager travels farther from home, eventually making real-time troubleshooting impossible. The spacecraft must increasingly rely on its own autonomous systems, designed decades ago with the limited computing power of the 1970s. Perhaps most remarkably, Voyager 1 continues to make scientific discoveries even as its systems slowly fail. The spacecraft has revealed that the boundary between our solar system and interstellar space is far more complex than previously imagined. The heliopause, once thought to be a simple boundary, appears to be a dynamic region where solar and galactic magnetic fields interact in ways that challenge our understanding of plasma physics. Voyager's instruments have detected unexpected variations in cosmic ray intensity and magnetic field orientation, suggesting that the interstellar medium has structure and variability that we're only beginning to comprehend. These discoveries underscore the profound value of Voyager's extended mission. Each additional year of operation provides insights into a realm that no other human-made object has ever explored. The spacecraft is writing the first chapters of interstellar physics, documenting conditions in a region of space that future missions may not reach for centuries. Every data packet transmitted back to Earth represents humanity's first direct sampling of the galaxy beyond our solar system. The trajectory of Voyager 1 carries it toward the constellation Ophiuchus, though it will be tens of thousands of years before it approaches another star system. Long after its transmitters have fallen silent, the spacecraft will continue its journey as a silent ambassador from Earth, carrying the golden record with its collection of sounds, images, and messages representing human civilization. In this sense, Voyager's mission transcends the limitations of its electronics, becoming a permanent artifact of human curiosity and ambition. Current projections suggest that we may receive signals from Voyager 1 until approximately 2025 to 2030, though this timeline depends on numerous factors, including the spacecraft's power management, the health of its transmitter, and the sensitivity of Earth-based receivers. The mission team continues to make difficult decisions about which systems to shut down and which to preserve, essentially triaging the spacecraft's remaining capabilities to maximize scientific return. The end of Voyager 1's communication will mark the conclusion of one of the most successful space missions in human history. For over 4 decades, this small spacecraft has served as humanity's most distant representative, exploring realms that exist only in the imagination of most Earthbound observers. Its journey from the launch pad at Cape Canaveral to the depths of interstellar space represents not just a triumph of engineering, but a testament to human curiosity and the drive to explore beyond familiar boundaries. When Voyager 1 finally falls silent, it will not represent a failure, but rather the natural conclusion of an extraordinary chapter in human exploration. The spacecraft will continue its journey through the galaxy, carrying with it the hopes and dreams of the civilization that created it. In the vast timeline of cosmic history, Voyager's active mission represents just a brief moment, but its legacy will endure as long as humanity remembers to look up at the stars and wonder what lies beyond. The silence that will eventually envelop Voyager 1 is not empty, but full of meaning. It carries within it the accumulated knowledge of decades of exploration, the ingenuity of thousands of engineers and scientists, and the collective curiosity of a species that refuses to be confined by the boundaries of its birth world. The mathematics of communication across the void are both elegant and unforgiving. As Voyager 1 continues its journey into the interstellar medium, each kilometer traveled adds another layer of silence to the conversation between Earth and our most distant ambassador. The spacecraft's radio signals, once strong enough to carry detailed images of Jupiter's swirling storms and Saturn's ethereal rings, now arrive as whispers barely distinguishable from the cosmic background noise. Picture, if you will, the radio waves emanating from Voyager's modest transmitter, spreading outward in an ever-expanding sphere. These electromagnetic pulses, carrying the precious data collected by the spacecraft's instruments, follow the inverse square law with mathematical precision. As the distance doubles, the signal strength becomes 4 times weaker. As the distance triples, it becomes 9 times fainter. This relentless mathematical relationship governs all communication across the cosmos, from the gentle murmur of distant pulsars to the fading voice of humanity's first interstellar probe. The Deep Space Network, that remarkable collection of radio telescopes scattered across 3 continents, strains to capture these diminishing signals. These massive dishes, each one a testament to human ingenuity, sweep across the sky with patient precision. Their sensitive receivers tune to frequencies that carry the whispers of worlds beyond our own. The largest of these antennas, stretching 70 meters across, can detect signals so faint they would be overwhelmed by the electromagnetic radiation from a single mobile phone on the moon. Yet even these technological marvels have their limits. The engineers who designed Voyager's communication systems understood this fundamental constraint from the beginning. They knew that distance would eventually silence the spacecraft's voice, that the expanding universe would gradually stretch the invisible thread connecting Earth to its most distant child. The question was never whether this silence would come, but when and how gracefully the conversation might fade. The spacecraft's power source, a radioisotope thermoelectric generator, provides the steady heartbeat that keeps Voyager alive in the cold emptiness of space. 3 plutonium-238 fuel cells, each no larger than a softball, generate electricity through the natural decay of radioactive material. This process, governed by the immutable laws of physics, produces a predictable decline in power output. Each year, Voyager's electrical systems receive slightly less energy than the year before, forcing mission controllers to make increasingly difficult decisions about which instruments to keep active and which to sacrifice to the growing darkness. The dance between power consumption and signal strength becomes more delicate with each passing year. The spacecraft's radio transmitter, operating at a mere 20 watts, draws a significant portion of the available power. For perspective, this is less energy than a typical household light bulb consumes, yet it must somehow bridge the gap between 2 points, separated by more than 20 billion kilometers. The engineering elegance lies not in brute force, but in careful optimization of every component, every circuit, every line of code that governs the spacecraft's behavior. As Voyager ventures deeper into interstellar space, the very medium through which it travels begins to affect its communications. The interstellar medium, that tenuous soup of gas and dust that fills the space between stars, is not truly empty. Though its density is far lower than the best vacuum achievable on Earth, it still contains enough particles to gradually influence radio waves traveling across vast distances. These particles scatter and absorb electromagnetic radiation, adding another layer of attenuation to signals that are already weakened by distance. The plasma waves detected by Voyager's instruments tell a story of the environment through which the spacecraft travels. These oscillations in the charged particles of interstellar space create a kind of cosmic weather that can affect radio communications. Solar storms, though now distant and weakened, still occasionally disturb the interstellar medium, creating interference patterns that can disrupt the delicate conversation between Earth and its wandering emissary. Mission controllers have developed increasingly sophisticated techniques to extract meaningful data from these weakening signals. Error correction algorithms, originally designed for Earthbound computer systems, have been adapted to recover information from transmissions corrupted by the noise of deep space. Multiple redundant systems ensure that critical data can be reconstructed even when significant portions of the signal are lost to interference or distance. The geometry of communication adds another layer of complexity to this interstellar conversation. As Voyager travels away from the Sun, Earth's position relative to the spacecraft changes continuously. Sometimes our planet is on the same side of the Sun as Voyager, providing a clear line of sight for radio communications. At other times, Earth passes behind the Sun from Voyager's perspective, creating a period of radio silence as our star's massive electromagnetic field blocks the fragile signals. The spacecraft's attitude control system, designed to keep its antenna pointed toward Earth, becomes increasingly critical as the signals weaken. Even a small misalignment can mean the difference between successful communication and complete silence. The gyroscopes that help maintain this pointing accuracy are themselves aging, their precision slowly degrading after decades of operation in the harsh environment of space. Temperature plays a crucial role in the longevity of Voyager's communication systems. The spacecraft's electronics, designed to operate in the extreme cold of the outer solar system, face new challenges as they venture into the even more frigid realm of interstellar space. Some components perform better in extreme cold, while others become less efficient, creating a complex balance that mission engineers must constantly monitor and adjust. The data rate from Voyager has already been reduced multiple times to accommodate the weakening signal, Where once the spacecraft could transmit detailed images and comprehensive scientific measurements, it now sends only the most essential information. Each bit of data becomes precious, carefully prioritized, and compressed to maximize the scientific return from these final years of operation. The protocols governing Voyager's communication have evolved over the decades of its mission. Originally designed for the relatively straightforward task of transmitting data during planetary encounters, these systems have been continuously updated and refined to handle the unique challenges of interstellar communication. Software updates, transmitted across billions of kilometers, have extended the spacecraft's capabilities far beyond what its original designers imagined possible. As we look toward the inevitable silence that awaits, we can appreciate the remarkable achievement that Voyager's communication represents. For over 4 decades, this small spacecraft has maintained contact with Earth across distances that dwarf human comprehension. Its voice, though growing fainter with each passing year, continues to carry the whispers of the interstellar medium back to the world that launched it on this epic journey. The final years of Voyager's communication will likely be marked by increasingly sporadic contact. Signals that once arrived daily may become weekly, then monthly, then cease altogether as the spacecraft's power reserves dwindle and the vast distances finally overcome our ability to bridge them. Yet even in this gradual fading, there is a profound beauty, a gentle conclusion to humanity's first conversation with the infinite darkness that lies between the stars. When that final signal is received, when the last whisper from Voyager fades into the cosmic background, it will mark not an end, but a transformation. As Voyager 1 continues its solitary journey through the vast emptiness of interstellar space, drifting ever further from the warmth and light of our sun, we find ourselves contemplating not just the spacecraft's remarkable achievements, but the profound questions that emerge from this unprecedented voyage into the cosmic unknown. The little probe that could, now more than 14 billion miles from home, carries with it the hopes and dreams of an entire species, a testament to human curiosity that refuses to be contained by the boundaries of our solar system. The spacecraft's trajectory through interstellar space follows a path that will take it toward the constellation Ophiuchus, though it will be tens of thousands of years before it passes anywhere near another star system. 6 light-years of this red dwarf star. To put this in perspective, this closest approach will still be nearly 10,000 times farther than the distance between our Sun and Pluto. The universe, it seems, has designed itself on scales that humble even our most ambitious technological achievements. But what does this mean for the continuation of Voyager's mission? As we've discussed, the spacecraft's power systems are steadily declining, with the radioisotope thermoelectric generator producing less electricity each year. The engineering teams at NASA have become masters of efficiency, carefully managing every watt of power, shutting down non-essential systems and instruments to preserve the most critical functions for as long as possible. It's a delicate balancing act, requiring decisions about which scientific instruments to keep operational and which must be sacrificed to extend the mission's overall lifespan. The Deep Space Network, that remarkable collection of radio telescopes scattered across the globe, continues its patient vigil, listening for Voyager's increasingly faint whispers from the depths of space. The signals traveling at the speed of light take over 22 hours to reach Earth, and by the time they arrive, they carry only a billionth of their original power. The fact that we can detect these signals at all represents one of the most remarkable achievements in the history of telecommunications, a testament to human ingenuity and the relentless pursuit of knowledge. Each day that passes brings new challenges for the mission controllers. The spacecraft's attitude control system, responsible for keeping Voyager properly oriented so its antenna can communicate with Earth, relies on small thrusters that fire in precise patterns to counteract the subtle forces acting on the spacecraft. These thrusters, designed to operate for perhaps 5 years, have now been functioning for over 4 decades, far beyond their intended lifespan. The fuel lines have become clogged with residue, requiring the team to switch to backup thrusters that haven't been used in decades, a process that requires careful planning and execution across the vast distances of space. The onboard computers, primitive by today's standards, but marvels of 1970s engineering, continue to function despite the harsh environment of space. These computers, with less processing power than a modern calculator, have endured decades of cosmic radiation, extreme temperature variations, and the general wear and tear of operating in one of the most hostile environments imaginable. Occasionally, cosmic rays strike the computer memory, causing what engineers call bit flips, where A1 becomes a 0 or vice versa. When this happens, the spacecraft's software must detect and correct these errors, a process that has become increasingly challenging as the systems age. The scientific instruments still operating on Voyager 1 continue to provide valuable data about the interstellar medium, that thin soup of gas and dust that fills the space between stars. The cosmic ray subsystem detects high-energy particles from distant stellar explosions, while the magnetometer measures the magnetic field that permeates our local region of the galaxy. The plasma wave instrument listens to the radio emissions generated by the interaction between the solar wind and the interstellar medium, providing insights into the complex boundary region where our solar system meets the galaxy at large. These measurements have revealed that interstellar space is not the empty void that scientists once imagined. Instead, it's a dynamic environment filled with charged particles, magnetic fields, and the remnants of ancient stellar explosions. The density of matter in interstellar space is incredibly low, with only a few atoms per cubic centimeter, making it a better vacuum than anything we can create on Earth. Yet, over the vast scales of the galaxy, this seemingly empty space contains enough matter to form new stars and planetary systems, continuing the cycle of cosmic evolution that has been ongoing for billions of years. As Voyager 1 moves through this environment, it encounters variations in density and composition that tell the story of our galactic neighborhood. The spacecraft has passed through regions where the interstellar medium is compressed by the shock waves of ancient supernova, and it has measured the helium abundance that reflects the nuclear processes that occurred during the Big Bang. These observations provide ground truth for our models of galactic evolution and help us understand how our solar system formed from the ashes of previous generations of stars. The temperature of interstellar space presents another fascinating aspect of Voyager's journey. While the kinetic temperature of the sparse gas is actually quite high, around 10,000 degrees Celsius, the effective temperature that Voyager experiences is much lower, around -270 degrees Celsius. This apparent contradiction arises because temperature, in the conventional sense, requires matter to collide and exchange energy. But in the near vacuum of interstellar space, such collisions are extremely rare. The spacecraft essentially exists in a state of thermal equilibrium with the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. The magnetic field measurements have revealed another layer of complexity in the interstellar environment. The galaxy possesses its own magnetic field, generated by the motion of charged particles and the rotation of the galactic disk. This field, though incredibly weak by terrestrial standards, plays a crucial role in shaping the paths of cosmic rays and influencing the formation of new stars. Voyager's measurements of this field's strength and direction provide valuable data for understanding the magnetic structure of our local galactic neighborhood. Perhaps one of the most poignant aspects of Voyager's continuing journey is the gradual loss of communication capability. As the spacecraft moves farther from Earth, the inverse square law ensures that its signals become progressively weaker. The Deep Space Network antennas must track the spacecraft with increasing precision, and the data rates must be reduced to ensure reliable communication. What once required minutes to transmit now takes hours, and the margin for error continues to shrink. The engineering teams have implemented increasingly sophisticated techniques to maintain contact with the spacecraft. They've switched to more sensitive receivers, implemented better error correction codes, and even changed the way commands are sent to account for the spacecraft's aging systems. Each successful communication session represents a small victory in the ongoing battle against distance and time. The power situation remains the most critical factor limiting Voyager's operational lifetime. The radioisotope thermoelectric generator was designed to provide power for the nominal mission duration of 5 years, but it has continued to operate for over 4 decades. The plutonium-238 fuel source has a half-life of 87 years, meaning that the power output decreases by about 4 watts per year. This steady decline has forced mission controllers to make difficult decisions about which systems to maintain and which to shut down. The heating systems that keep the spacecraft's instruments warm have been among the first casualties of the power decline. As these heaters are turned off, the instruments experience increasingly cold temperatures, pushing them beyond their designed operating limits. Remarkably, many continue to function despite these harsh conditions, though their performance may be degraded and their reliability reduced. The attitude control system, essential for maintaining communication with Earth, remains one of the highest priorities for power allocation. Without proper orientation, the spacecraft's antenna cannot point toward Earth, and communication would be lost entirely. The system relies on reference points provided by the Sun and the star Canopus, though as the spacecraft moves farther from the Sun, these references become increasingly difficult to use. Current projections suggest that Voyager 1 will lose the ability to communicate with Earth sometime between 2025 and 2030, though the exact timing depends on the health of the spacecraft's systems and the efficiency of power management. When that moment arrives, Voyager will continue its journey in silence, carrying its precious cargo of scientific instruments and the golden record into the depths of space, a message in a bottle cast into the cosmic ocean. The golden record, that remarkable compilation of sounds and images from Earth, will outlast the spacecraft itself by billions of years. Constructed from gold-plated copper, it's designed to survive the harsh environment of space for millions of years, waiting for the unlikely but possible encounter with an alien intelligence. The record contains music from cultures around the world, greetings in 55 languages, and sounds of Earth ranging from thunder and surf to the songs of whales and the laughter of children. Even after communication is lost, Voyager 1 will continue to provide valuable scientific data about the nature of interstellar space. The spacecraft's trajectory and any deviations from its predicted path will offer insights into the gravitational environment of our galactic neighborhood. Future space telescopes may be able to observe the spacecraft as it travels through interstellar space, providing a unique perspective on the dynamics of our local stellar environment. The legacy of Voyager 1 extends far beyond its scientific achievements. The spacecraft has fundamentally changed our perspective on our place in the universe, showing us that the solar system is not an isolated island, but part of a vast galactic ecosystem. The famous pale blue dot image, taken as Voyager 1 was leaving the solar system, captured Earth as a tiny speck of light suspended in a sunbeam, a humbling reminder of our planet's fragility and the importance of preserving our cosmic home. As we contemplate Voyager's future, we're also planning for the next generation of interstellar missions. The lessons learned from Voyager's journey are informing the design of future spacecraft that will venture even deeper into the galaxy. These missions will benefit from advances in nuclear power sources, more efficient communication systems, an improved understanding of the interstellar environment gained from Voyager's pioneering observations. The Voyager program has also inspired a new generation of scientists and engineers, demonstrating that ambitious goals can be achieved through careful planning, innovative engineering, and persistent dedication. The mission has shown that humanity can reach beyond the boundaries of our solar system, that we can send our representatives to explore the galaxy and report back on what they find in the vast spaces between the stars. In the quiet moments of the night, as Voyager 1 continues its solitary journey through the cosmic dark, we might imagine the spacecraft as humanity's most distant ambassador, carrying our hopes and dreams into the unknown. The vast emptiness between stars presents challenges that dwarf anything Voyager 1 encountered in our solar system. Out here, in the realm astronomers call the local interstellar medium, the spacecraft drifts through a sea of hydrogen atoms so sparse that a single cubic centimeter contains fewer particles than the best vacuum chambers on Earth. Yet even in this near-perfect void, Voyager continues its patient work, sampling the cosmic wind that flows between the stars. The interstellar medium isn't uniform. It's a complex tapestry of gas clouds, some hot and thin, others cool and dense. Voyager has already detected variations in the magnetic field, strength and direction, subtle changes in the density of charged particles, and fluctuations in the cosmic ray environment. These measurements are painting the first detailed portrait of our local stellar neighborhood, revealing how our sun's influence gradually fades and gives way to the broader galactic environment. Scientists have discovered that the boundary between our solar system and interstellar space isn't sharp, but rather a gradual transition. The heliopause, that boundary Voyager crossed in 2012, represents where the solar wind finally surrenders to the pressure of interstellar space. But even beyond this boundary, the sun's influence lingers. Voyager's instruments detect particles that were accelerated at the heliopause, cosmic rays that have been modified by their journey through the outer solar system, and magnetic field lines that may still connect to our distant star. The temperature in interstellar space hovers around -270 degrees Celsius, just 3 degrees above absolute zero. At these temperatures, hydrogen atoms move sluggishly, and the thermal environment is so cold that even the spacecraft's radioactive power source seems almost tropical by comparison. Yet Voyager's instruments continue to function, their electronics warmed by the gentle decay of plutonium-238, a process that has remained remarkably stable for over 4 decades. Power management has become the mission's greatest challenge. The spacecraft began its journey with about 470 watts of electrical power, enough to run a small household appliance. Today, that power has diminished to roughly 240 watts, barely enough to illuminate a few light bulbs. Mission engineers perform a delicate balancing act, shutting down non-essential systems to preserve power for the most critical instruments. They've turned off heaters, shut down redundant systems, and even disabled the thrusters that once kept the spacecraft's antenna pointed toward Earth. The signal from Voyager 1 now takes over 22 hours to reach Earth, traveling at the speed of light across a distance that continues to grow by about 500 million kilometers each year. When mission controllers send a command to the spacecraft, they must wait nearly 2 days for confirmation that it was received and executed. This communication delay adds another layer of complexity to operating a spacecraft that's already pushed far beyond its design limits. The strength of Voyager's radio signal has diminished according to the inverse square law, meaning that as the distance doubles, the signal becomes 4 times weaker. Ground-based radio telescopes strain to detect these faint whispers from the edge of known space. The Deep Space Network, NASA's array of massive radio dishes scattered across the globe, must focus their attention with laser-like precision to capture Voyager's increasingly faint transmissions. Engineers estimate that Voyager 1 will fall silent sometime between 2025 and 2030, when its power output drops below the threshold needed to operate its radio transmitter. The exact date depends on various factors: how efficiently the remaining instruments use power, whether any systems fail prematurely, and how quickly the plutonium continues to decay. It's a race against time, with mission scientists working to extract every possible piece of data before the inevitable silence. But even after its voice fades, Voyager 1 will continue its journey. The spacecraft carries enough momentum to keep traveling for millions of years, gradually climbing out of the sun's gravitational well and into the broader galaxy. 6. Light years of the star AC, plus 79 degrees 3888, a red dwarf in the constellation Camelopardalis. To any inhabitants of that stellar system, Voyager would appear as a small, dark object drifting silently through their cosmic neighborhood. The golden record attached to Voyager's side will outlast the spacecraft itself by eons. Made of gold-plated copper, it's designed to remain readable for billions of years. The record contains sounds and images from Earth, whale songs, human voices speaking in dozens of languages, music from Bach to Chuck Berry, and photographs depicting life on our planet. It's humanity's message in a bottle, cast into the cosmic ocean with the hope that someday, somewhere, intelligent beings might find it and learn that we once existed. The scientific legacy of Voyager 1 extends far beyond its immediate discoveries. The spacecraft has fundamentally changed our understanding of the outer solar system and our place in the galaxy. Its observations of Jupiter's turbulent atmosphere revealed weather patterns that dwarf anything on Earth. Its images of Saturn's rings showed them to be far more complex than anyone had imagined, with thousands of individual ringlets shepherded by small moons. The discovery of active volcanoes on Io and evidence of subsurface oceans on Europa revolutionized our thinking about where life might exist in the solar system. Perhaps most importantly, Voyager 1 has given us a new perspective on our cosmic environment. Before its journey, the heliosphere was largely theoretical, a bubble of solar influence that we knew must exist but had never directly measured. Voyager's crossing of the heliopause marked humanity's first direct sampling of the interstellar medium, turning speculation into scientific fact. The spacecraft has revealed that our solar system isn't isolated, but intimately connected to the broader galactic environment. The mission has also demonstrated the remarkable durability of human engineering. Voyager 1 was built with 1970s technology, using computer systems less powerful than a modern smartphone. Yet it continues to operate in an environment more hostile than any on Earth, enduring decades of cosmic radiation, extreme temperatures, and the vacuum of space. The spacecraft's longevity is a testament to the skill and foresight of the engineers who designed it, as well as the dedication of the mission controllers, who have kept it running for over 4 decades. As we approach the end of Voyager 1's active mission, scientists are already planning for the next generation of interstellar probes. Future missions might use advanced propulsion systems to travel faster and farther, or they might be designed specifically to study the interstellar medium, rather than touring the outer planets first. Some proposals envision swarms of small spacecraft, each carrying specialized instruments to study different aspects of the space between stars. The approaching silence of Voyager 1 marks not just the end of a mission, but the end of an era. This spacecraft has been our ambassador to the cosmos for longer than many people have been alive. It has sent back images and data that have inspired generations of scientists, engineers, and dreamers. When its transmissions finally fade, we'll lose our only direct connection to the interstellar realm, at least until the next generation of deep space explorers begins their own journeys. Yet in another sense, Voyager 1's mission will never truly end. The spacecraft will continue its journey long after Earth itself has changed beyond recognition. It will drift through the galaxy as a monument to human curiosity and ingenuity, carrying with it the golden record and the hopes of a species that dared to reach beyond the boundaries of its home world. As we journey further into the cosmic depths, we encounter one of the most remarkable phenomena in our universe's grand architecture: the delicate dance of orbital mechanics that governs not just our own solar system, but but countless others scattered throughout the galaxy. These celestial choreographies reveal gravity's most intimate artistry, where precision meets poetry in the vast theatre of space. Consider the extraordinary symphony playing out in our cosmic neighborhood. Right now, as you rest comfortably in your bed, you are participating in multiple gravitational waltzes simultaneously. The Earth spins beneath you at over 1,000 kilometers per hour, yet you feel only the gentle embrace of gravity keeping you safely anchored. Our planet races through space at 30 kilometers per second as it orbits the Sun, maintaining that perfect balance between falling toward our star and flying off into the cosmic void. This balance is not accidental, but rather the result of billions of years of gravitational fine-tuning. In the early solar system, chaos reigned supreme. Countless planetary embryos collided and merged in violent cosmic ballet, their orbits unstable and unpredictable. Yet from this apparent disorder emerged the elegant stability we observe today, as gravity slowly shepherded these wandering worlds into their current harmonious arrangement. The mathematics underlying this cosmic choreography is breathtakingly beautiful. Johannes Kepler first glimpsed these patterns in the early 17th century, discovering that planets sweep out equal areas in equal times as they orbit the Sun. This revelation spoke to a deeper truth about the universe, that celestial motion follows precise mathematical laws, creating predictable patterns that repeat across cosmic time. But gravity's artistry extends far beyond simple orbital mechanics. Throughout our solar system, we find examples of what astronomers call resonance, where gravitational forces create stable mathematical relationships between orbiting bodies. Jupiter's moons, Io, Europa, and Ganymede, perform an intricate dance where their orbital periods maintain exact ratios, creating a cosmic music box that has played the same melody for billions of years. These resonant relationships aren't mere curiosities, but fundamental organizing principles that appear throughout the galaxy. As we've discovered thousands of exoplanets orbiting distant stars, we found that many of these alien worlds are locked in similar gravitational embraces, their orbits synchronized in mathematical harmony that speaks to the universal nature of these cosmic laws. The precision of these orbital relationships allows us to peer into the past and future with remarkable accuracy. We can calculate exactly where Mars will be 1,000 years from now, or predict eclipses centuries in advance. This clockwork precision has enabled us to send spacecraft on incredible journeys, using gravitational assists from planets to fling our robotic explorers to the outer reaches of the solar system and beyond. Perhaps most remarkably, these same gravitational principles that govern planetary motion also orchestrate the grand architecture of galaxies themselves. Our Milky Way rotates like a cosmic pinwheel, its spiral arms maintained by density waves that sweep through the galactic disk. Stars orbit the galactic center in complex patterns, occasionally diving into the spiral arms where they encounter the raw materials needed to birth new stellar companions. Even our galaxy participates in larger gravitational dances. The Milky Way and its neighbor Andromeda are slowly approaching each other in a cosmic waltz that will culminate in their merger some 4 billion years from now. This galactic collision will reshape both stellar cities, creating new orbital patterns and perhaps triggering bursts of star formation that will light up the merged galaxy like cosmic fireworks. These gravitational relationships extend outward to encompass the largest structures in the universe. Galaxy clusters, containing thousands of individual galaxies, move through space in their own stately processions. The cosmic web itself, that vast network of dark matter filaments stretching across billions of light years, channels the flow of ordinary matter and guides the formation of new structures according to gravity's patient blueprint. What makes this cosmic choreography so profound is its universality. The same inverse square law that governs the fall of autumn leaves also determines the orbits of distant exoplanets. The tidal forces that create Earth's ocean rhythms also sculpt the rings of Saturn and stretch the surfaces of Jupiter's moons. Gravity speaks a universal language that connects every scale of cosmic structure. As we continue to explore the universe with ever more sophisticated instruments, we're discovering that gravitational dances occur in the most extreme environments imaginable. Around black holes, space and time themselves become part of the choreography, with matter spiraling inward along paths that trace the curvature of space-time itself. The collision of such massive objects creates gravitational waves that ripple outward at the speed of light, carrying information about these cosmic dances to sensitive detectors here on Earth. The beauty of gravity's choreography lies not just in its mathematical elegance, but in its role as the architect of complexity. Without gravity's patient work over billions of years, there would be no stars to forge heavy elements, no planets to provide stable environments for life, no galaxies to organize matter into the structures we observe today. Every breath you take, every heartbeat that marks the passage of time, occurs within the embrace of gravitational forces that have shaped the cosmos since its earliest moments. As you drift deeper into sleep, carried by Earth through its orbit around the Sun, remember that you are part of this grand cosmic dance. The same forces that ignited the first stars and will guide the last planets in their orbits around dying suns are gently holding you now, ensuring that your dreams unfold in the safety of gravity's eternal embrace. The silence that awaits Voyager 1 is not the absence of sound, for sound has never traveled through the vacuum of space. Rather, it is the silence of communication, the gentle fade of our final technological whisper into the cosmic dark. This silence carries with it a profound melancholy, yet also a strange comfort, like watching a loved one drift peacefully into sleep. As we contemplate this eventual quiet, we might consider what it means for a creation of human hands to venture so far beyond our reach. Voyager 1 has become something unprecedented in our history, a piece of Earth that will outlast our cities, our civilizations, perhaps even our species. While empires rise and fall, while mountains erode and oceans shift, this small spacecraft will continue its patient journey through the galaxy, carrying with it the golden record, our message in a bottle cast into the cosmic ocean. The mathematics of its trajectory are beautifully simple. Voyager 1 moves at approximately 17 kilometers per second relative to the Sun, a velocity that seems tremendous by earthly standards, yet appears almost leisurely against the vast scales of interstellar space. To reach the nearest star, Proxima Centauri, would require more than 73,000 years at this speed. But Voyager 1 is not headed toward Proxima Centauri. Instead, it follows a path that will take it roughly in the direction of the constellation Ophiuchus, where it will pass within about 2 light-years of the star AC Plum 79 3E888 in approximately 40,000 years. The golden record, that extraordinary collection of sounds and images from Earth, will by then have been silent for tens of thousands of years, yet it will remain a time capsule of our world as it was in 1977, when disco filled the airwaves and the first personal computers were beginning to appear in homes. The record contains the sound of wind and rain, the calls of whales and birds, music from Bach and Beethoven, Chuck Berry, and traditional folk songs from around the world. It holds greetings in 55 languages, from ancient Sumerian to modern Chinese, each one a voice reaching across the void to say simply, "We were here, we wondered, we reached out." By the time we lose contact with Voyager 1, this record will have become something far more precious than when it was first attached to the spacecraft. It will be the last remnant of Earth's voice in the cosmos, continuing its journey long after our radio signals have faded. The poignancy of this transition, from active communication to silent testimony, speaks to something fundamental about the human condition: our desire to leave traces of ourselves in the universe, to matter beyond our brief existence. The spacecraft itself will undergo a gradual transformation as it travels deeper into interstellar space. 7. Kelvin, just a few degrees above absolute zero. Metal components will contract and potentially become brittle, though in the absence of atmospheric corrosion, much of the structure will remain intact for millions of years. Micrometeorites, those tiny specks of dust that pervade space, will occasionally strike the spacecraft, creating microscopic craters and gradually eroding its surface. Over geological timescales, these impacts will slowly wear away the outer layers, but the process is so gradual that even after 1 million years, the spacecraft will remain largely recognizable. The golden record, protected by its aluminum cover, will likely survive even longer, its information potentially readable for billions of years if ever discovered by an alien civilization. The silence that follows the end of our communication with Voyager 1 will be profound, but it will not be empty. It will be filled with the weight of achievement, the satisfaction of having pushed the boundaries of human exploration further than ever before. When that final signal fades, when the last data packet is received and decoded, we will have witnessed something unprecedented in human history, the first human-made object to journey beyond our solar system and into the galaxy proper. This transition from communication to silence mirrors the natural rhythms of the cosmos itself. Stars shine brightly for billions of years before gradually dimming and cooling. Galaxies merge and separate in vast cosmic dances that play out over unimaginable timescales. Even the universe itself may eventually reach a state of maximum entropy, a cosmic silence where no more energy remains to power the processes that create light and warmth and life. Yet in this seemingly bleak cosmic perspective, Voyager 1 represents something extraordinary, a defiance of entropy, a small spark of intelligence and purpose, continuing its journey through the dark. It is a testament to the remarkable ability of conscious beings to transcend their immediate circumstances, to create something that outlasts them, to touch eternity in however small a way. The question of how far Voyager 1 can go before we lose contact has a concrete answer measured in distance and time, but it also has a deeper meaning. It asks us to consider what it means to reach beyond ourselves, to extend our presence into the universe in ways that transcend our biological limitations. In this sense, Voyager 1 will continue going long after we lose contact, carrying with it not just our scientific instruments and golden record, but our dreams of exploration, our curiosity about the cosmos, our hope that somewhere in the vast darkness, other minds might one day discover our small gift to the universe. The silence that awaits is not an ending but a transformation, a passage from one phase of the mission to another, from active exploration to passive testimony, from real-time communication to timeless message, from human creation to cosmic citizen. In this transformation, Voyager 1 will join the ranks of the most enduring human achievements, standing alongside the Great Pyramids and the works of Shakespeare as something that speaks to the best of what we can be. As our cosmic journey through the void draws to its gentle close, we find ourselves at the threshold of understanding something profound about humanity's place in the grand tapestry of existence. Voyager 1, that intrepid messenger we followed through the outer darkness, carries within its mechanical heart not just scientific instruments, but the very essence of what it means to be human. The golden record, that gleaming disk of copper and gold, represents perhaps our species' most thoughtful attempt at cosmic communication. Encoded upon its surface are the sounds of Earth, the voices of humanity, the mathematical principles that govern our understanding of the universe. It's a love letter to the cosmos, a declaration that we were here, that we wondered, that we reached beyond our small blue world to touch the infinite. But the record is more than mere data. It contains the laughter of children, the music of Bach and Beethoven, the gentle patter of rain on leaves. It holds the greeting of a whale song, the rhythm of a human heartbeat, the whispered words of love in dozens of languages. These sounds, now traveling through the interstellar medium aboard our silent ambassador, will outlast our civilizations, our continents, perhaps even our sun itself. Consider the profound melancholy of this journey. Voyager 1 drifts through a realm where the very concept of weather ceases to exist, where the familiar cycles of day and night become meaningless abstractions. The spacecraft that once danced through the gravitational fields of Jupiter and Saturn now moves through a medium so tenuous that a single breath of Earth's atmosphere contains more particles than Voyager encounters in millions of kilometers of travel. Yet this emptiness is not truly empty. The interstellar medium whispers with ancient stories, carries the breath of stars that died before our sun was born, holds the seeds of future stellar nurseries. Through this cosmic gossamer, Voyager continues its eternal voyage, its instruments still functioning, still measuring, still reporting back to us across the growing gulf of space and time. The signals that reach us from Voyager grow ever fainter, like the voice of a friend walking away into fog. Each transmission requires increasingly sensitive equipment to detect, increasingly sophisticated mathematics to decode. The Deep Space Network, that marvel of human engineering, strains to catch these whispers from the edge of everything we know. But the silence that awaits is not defeat. It is transformation. When Voyager's last signal finally fades into the cosmic background radiation, when its radioisotope thermoelectric generators can no longer power its transmitters, the spacecraft will continue its journey in perfect silence. It will become a monument to human curiosity, a testament to our species' irrepressible desire to explore, to discover, to understand. In the deep future, when our sun has swollen into a red giant and cooled to a white dwarf, when the Earth itself has become a memory, Voyager will still be traveling. It will sail between the stars for millions of years, perhaps billions, carrying its precious cargo of human culture through the galaxy. The golden record will endure, a time capsule of a species that dared to dream beyond the boundaries of their world. There is something profoundly humbling about this perspective. We who worry about quarterly reports and traffic jams, who fret over social media notifications and grocery lists, are part of a species that built a machine capable of traveling to the stars. We are the children of the same minds that conceived the golden record, that calculated the gravitational assists needed to fling a small piece of Earth into the cosmic ocean. The story of Voyager is ultimately the story of us. It reflects our greatest strengths and our deepest longings. We are explorers by nature, wanderers who look at the horizon and wonder what lies beyond. We are scientists who seek to understand the fundamental principles that govern existence. We are artists who find beauty in the dance of planets and the song of pulsars. As you drift towards sleep tonight, carried along by Earth's rotation through the star-filled darkness, remember that you are part of this cosmic story. The same atoms that form your thoughts were forged in the nuclear furnaces of ancient stars. The same curiosity that drives you to wonder about the universe also propelled Voyager beyond the edge of our solar system. In the morning, when you wake to sunlight streaming through your window, Voyager will still be out there, still traveling, still carrying our message to the stars. It will continue its journey long after we are gone. A lasting testament to the human spirit of exploration and discovery. The universe is vast and mysterious, filled with wonders we can barely imagine. But we are not mere observers of this cosmic drama. We are participants, explorers, dreamers who build machines to carry our hopes and dreams across the infinite darkness. In Voyager's endless journey, we see reflected our own deepest aspirations, our own quiet determination to reach beyond the boundaries of the known and touch the face of eternity. Sleep well, knowing that somewhere in the darkness between the stars, a small piece of humanity continues its eternal voyage, carrying our stories, our music, our laughter into the cosmic night. The universe is listening, and we have given it our voice.